It's time to move on and dive deeper into Go. In this course section, we are going to explore functions. We are going to explore this key Go feature and learn what exactly functions are and how we write custom functions. We are going to then see how we can configure and tweak functions to meet our requirements with help of parameters and return values. And we are going to dive into this special Go feature, which we don't have in a lot of other programming languages, where functions are not limited to returning a single value, but may actually return multiple values. Now, before we dive into any code, let's answer an important question first. What exactly is a function in programming and in Go specifically? I personally like to explain functions as code on demand. A function is a construct, not just in Go, but in all programming languages in the end, that allows us to define some code ahead of time. So code that should not be executed right away when it's parsed, but instead which should be saved to be executed later. And the code should then be executed once you call a function, which is simply the usage of a special syntax in your code. Once that happens, the function code executes. And then functions allow you to not just execute code at a certain point of time, and possibly also multiple times, but you also have rich configuration options, and you can but don't have to accept input with a concept called parameters, which we'll explore in this section, and you can but don't have to produce output, which we call return values. And we're going to explore all of that in this section, but that is, in theory, what a function is in programming and in Go specifically. Now, we already saw one function in action plenty of times in this course already, and that was the main function. And in general, in Go, you create a function by using the func keyword that tells Go that you want to create a function. Then you pick any name of your choice, though the main name is special. I'll come back to it in a second, but generally it's up to you. Then you have parentheses, and we can add something between those parentheses. We'll also do this in this course. And then you have opening and closing curly braces, and between those curly braces, you have the so-called function body. You have that code that should not execute immediately, but only once the function is called. Now, the main function is a special function, as I explained before. It's a function which you don't call yourself, but instead which will be executed by the Go engine, if you want to call it like this, once you run this Go program. And it's the main entry point of the program, so main is kind of a reserved and special word. But in this section, we're going to add more functions, and for those functions, the names will be up to you. Now, when it comes to calling a function and how that looks like, we might not be doing it for main, but we are doing it here in line 6 with println. A println is a function built into the format package, so provided by the format package, and we execute a function by referring to its name and then adding opening and closing parentheses after that name, potentially, as we have it here, with a value or even multiple values between those parentheses, which are then provided as input to that function. But again, that is something we'll explore in greater detail throughout this section. Now, that is a basic function, which we saw plenty of times before. In this section, we're now going to write our own functions, and we are going to learn about different ways of writing these functions and using these functions. So let's dive right in, and let's write a second function. Let's say here in the main function, we don't just want to output this dummy text, but the sum of two numbers. So we could have the numbers a and b. A is 5 maybe, and b is 10. And the concrete values here are hard-coded into the code by me. So I'm just locking them into the code here. I'm just writing them as a developer. Of course, in a real program, we might be fetching them from the command line, from some user input, as we did it in the BMI calculator example in the previous section. I just want to save some time regarding that, and hence here I'll just use 2 dummy values. Now we might want to add them together, and of course for that we could add a sum variable and just add a plus b like that, and then work with that variable. But maybe adding 2 numbers together is such a common operation, which we perform so often in our code, that we want to define a short custom command, which is in the end what a function is, that we can then re-execute over and over again, and we don't have to write this code over and over again. Because of course, for demo purposes, this is a rather simple piece of code, and writing it over and over again wouldn't be too hard, but nonetheless, we might want to outsource it into a custom command, which we can just execute. Also, so that if we ever change this to a subtraction, we don't have to do that in 10 different places of our code if we had that code snippet in 10 different places. But instead, we only have to do it once in our custom function, and then all the places where we refer to that function will automatically use that updated code. So that could be another reason why we might want to outsource it. And hence here I'll add a second function, and we can add it in front of main or after main. It does not matter. Here I'll add it after main, and I'll name it add. Now I did mention that the function name is up to you, with the exception of the main function, and then the function name should describe what the function does. So in case of variables and constants, you typically want to describe what's stored in the variable or constant. In the case of functions, you instead want to describe what the function does. And if this function adds 2 numbers, add sounds like a fitting name. Then we add opening and closing parentheses and then curly braces. And now here we could move that code into that function and do that calculation in here. But now we'll face a couple of problems. For example, we have those red squiggly lines on A and B. And the reason for that is that A and B are variables in the main function and therefore only available in there. If you don't define variables as global variables, they by default are only available in the function in which you defined them. And hence A and B are not available in add. Now, of course, we could turn them into global variable so that we're able to use them in all functions, but it's generally not considered a good practice to make all your variables global. Instead, you want to narrow down the scope as much as possible. In addition, this function should also work standalone and not depend on any global variables, because if we would depend on such variables, it would mean that anything that changes those variables anywhere in the program potentially changes how that function behaves. And that's also something we typically want to avoid. And that's where function input, so-called parameters, come into play. Functions don't have to take parameters. For example, the main function receives no input, but they may take parameters. And we make it clear that a function should accept some input, so-called parameters, by adding them between those parentheses here right after the function name in the function definition. Here we can accept any amount of parameters we want to accept, and we can give them any names of our choice. For example, num1 for the first number and num2 for the second number. This then creates variables that are only available in that function, but variables that can be set when that function is called. Something we'll do in a second. A println does the same internally. It basically accepts the output text as a parameter, and when we call the function, we pass in the concrete value for that parameter that will then be used inside of that function. And here we're doing the same. We are defining that this function takes 2 parameters, which will be set once that function is called. Now num1 and num2 are now available like local variables inside of that function, but still we're getting some errors here. And the reason for that is that Go is still a language that's all about types, about value types. And just as we have to define types when we declare variables or provide an initial value from which the type can be inferred, as it's the case here, we also have to define the types for our parameters. Because here, Go at the moment has no chance of knowing which kind of value type will be used for num1 and num2, and that's not allowed. So to make it clear which types of values we'll get here, we should again add the type identifier after the parameter name, just as we added after the variable name if we use that longer variable definition syntax we saw earlier in the course. So here I know that, for example, I want to work with integers, and hence here I'll add int after num1 and num2. And now it's clear to Go that we'll get some integer values here. Of course, we could also accept floats if that makes more sense for us here, but I'll go with int. Now with that, we can calculate the sum, which is also of type int since we add two integers. And with that, add does its job. But we calculate the sum, and at the moment, sum is a variable that's only available inside of add. As I explained before, a variable defined in a function is only available inside of that function. We could fix it by using global variables, but as mentioned, that's not recommended. You should avoid that. And therefore, instead, what we want to do to make that result available outside of this function as well, in the place where the function will be called, we typically return a value by adding a return statement, by adding this return keyword. Now, just like parameters, you don't have to add a return statement. The main function, for example, has neither parameters nor a return statement. And that's absolutely fine as well. You can have functions without both. You can have functions with parameters but without return statements. And you can have functions without parameters but with return statements. Here we have a function that will have both parameters and a return statement. And here I return sum. So I return the value stored in this variable. But again, I get an error with that. And the error I get here in the end is that this function, the add function, in the end doesn't expect any results, any returned values. Because in Go, you need to make it clear if a function will have a return value or not. And you don't just make that clear by simply throwing in a return statement. Instead, you have to add a little annotation after this parameter list here. Here, you have to define the type of value this function might return. So if this function returns an int, you should add int here. Just as you add the type after a parameter or a variable, here we add the type of value created by the function after the function definition, so after the function name and the parameter list. And now this is a valid function that makes it very clear that it wants two numbers, two integers as parameters, and that it will generate and return an integer. And hence we then have to return such an integer here. And of course, instead of writing this in 2 lines, we could also shorten this and just write 1 line and get rid of that second return statement here. Now we have that add helper function, and now back in main, we could re-add our sum, but now produce it by calling add and passing A and B to add, like that. And then instead of printing this dummy text, here we could output the sum. And that would now be a short first program that actually uses a custom function in addition to that main function to do its work. Of course, it's still a dummy function. As mentioned before, for this simple operation, we could argue whether we want it or not, but it's a great example for getting into functions and to understand how they generally work. And therefore now if we try to run this module, which I created here, I get 15 as an output here, which indeed is the result of adding 5 and 10 together. Now I mentioned it before. Functions can but don't have to take parameters, and they can but don't have to return values. And therefore, let's write a second function. And I want you to write this function on your own, simply to practice this a bit more. You should write a function with any name that makes sense to you that actually just prints a new line, and it should print the input that function receives. So that's your job. As a simplification, that function should only work with integer inputs, so no other types, since we don't know yet how we could accept different types. So only integer inputs should be supported, and then the function should take an input and print it to the command line. Try this on your own first. I'll give you a few seconds to pause the video and try it on your own, and then we'll implement this together. So, did you succeed? Let's now write such a function together. And again, it will of course be a rather simple function. Later, we'll also have more complex functions, but it's a great practice. Below the add function, though the position doesn't matter, I'll add the print number function. The name is up to you, but again, you should describe what that function does, and that function will in the end deal with outputting a number. So here, I'll then add my parentheses and the curly braces, and then I mentioned that this function should take an input, a parameter, therefore. And here I'll name it number, and I mentioned that we should only accept integers for now, so I'll make that of type int. And between the curly braces, we can now output that number. And for that, of course, I can just grab this line of code from line 11, println, cut it, and add it here, and then output number. Again, it's a rather useless function since it just wraps one line of code, you could say, but it is a good practice. The interesting thing about this function is that that's a function that takes a parameter but doesn't return anything, because it doesn't need to. It just prints something to the command line. And therefore we don't add any type after the function name and the parameter list, just as we didn't have anything after main. Now inside of name, we can now call print number, this function we just added, and then pass our integer number to it. And to make that function a little bit more useful, though that's of course optional and probably not something you did, we can of course switch from println to printf instead, and then format this in a more detailed way, so with richer formatting options, and for example say the number is, and then %v, and then output number like that. Now we added at least a little bit of extra utility to this custom function. And hence now with that, if I run this module again, I get the number is 15, output like that. So that is working, and that's now a second custom function in action, this time a function with parameters or with one parameter, but without a return value. So the basic idea and syntax behind functions should be clear. Let's now dive into a special feature of Go, which we don't have in all programming languages. In Go, functions can return multiple values. Now, with that, I don't mean that you can have return multiple times in the same function. If I return this, for example, that would not work because this return statement, the second one, is never reached. Because once you execute this return keyword, so to say, once this line of code is reached, the function execution stops and any code thereafter is not executed. So that's not how it works. But you can return multiple values by comma separating them in the line where you use the return keyword. Now for the add function, that doesn't make a lot of sense, but what about these numbers? What if we would want to generate some random numbers here? For that, we can add another function, generate random numbers, sounds like a good name. And that's a function that actually doesn't take any input, let's say, but it should return values, and it should return two values, two numbers. Now, first of all, we need to generate the random numbers. And for that, we can use another built-in package provided by Go, and that's the rand package. And here we got two packages called rand. We need the one from moth. So if we select this one from moth/rand and hit tab, this import gets added. And now that's still a package, even though there is a slash here. It's basically a package inside of another package, you could say. You can create such packages on your own if inside of a package subfolder you add another subfolder which contains then yet another package. And that's what's happening here. We have the moth package, and that has the rand sub package. Now this is a package built into Go which gives us a lot of utility functions that deal with generating random numbers. We access them through a dot as before, and then here we got the int n function, and here we see a little explanation about this function. In the end, this is a function that takes one parameter, so it's a function built into Go that takes one parameter, as we can tell, of type int. And then it will produce a non-negative random number between 0, which is included, and n, which is excluded. So that number which we pass here is not an actual result we can get, but up to that number we can get any integer. And it will then return that random number which it generated. So here we call this function by adding the parentheses. And since we want a parameter value here, we pass it, and that should be a non-negative integer, and I'll just pass in 10 here to generate a random number between 0 and 10, 10 excluded. Now this returns an integer as we learned, and therefore I'll have my random number 1, which I store here, and then I repeat that to generate a second random number. So now I have two variables here inside of this function for two different random numbers. And of course, they could also be the same. They will be recalculated every time we call this function. And every time we do that, brand new random numbers will be generated. Now I want to return both numbers, and that's now the special thing about Go. We can add our return statement here, and where in many other programming languages you can only return one value here, in Go you can return random number 1 and then add a comma and also return random number 2. Now we just have to adjust our function definition here and make it clear that we will return two values which each are of type int. And we do that by adding another pair of parentheses here after the function name and the parameter list, which is empty, but which we still need to add. And there we now add the types of all our return values, int and int separated by a comma. If you only have one return value, you don't need the wrapping parentheses, then you would just add int like this. But if you have more than one return value, you need to wrap those return value types in parentheses and then list them as a comma-separated list inside of these parentheses. And now we have this generate random numbers function that produces more than one result. Now, of course, in other languages, like for example JavaScript, we also have workarounds, which still in the end allow us to return multiple values. For example, in JavaScript, we can return a single value, which is an array, which is a special value, which also exists in Go, which we'll explore later, which is one value that can then internally store more than one values. So with that, we return one value in the function, but that one value holds multiple values. And we can do something similar in Python. There, it even looks very similar to what we do in Go. This is a so-called tuple. It's also one value, just as the array in JavaScript, but it's one value with multiple values internally. So there are ways in other programming languages as well, but in Go, it's built in just like that. But with that, we got our generate random numbers function. And now we can call that here to produce these random numbers here in the main function. For that, we call the function as we learned it, by using its name and adding parentheses thereafter. And now generate random numbers returns two values. So we can of course create our a variable, but that's not enough if we just store it in a. Instead, now we get two return values. Hence, if we want to store them in variables, we also need to create two variables. And we can do that by simply adding a comma here on the left side of the colon equal sign operator, and then list all the variables we want to create here. It would also work, by the way, if we just use the equal sign operator for existing variables. We can then also reassign multiple values to multiple variables in one go. The syntax would be the same, just without the colon. But here we create brand new variables, and we create multiple new variables in one step for these different return values returned by generate random numbers. With that, if we now run this code, we'll get a different result. However, at the moment, we'll get the same result every time we run this, and that just has something to do with how this rand package and the random functions in there work. In order to produce different numbers every time we run this program, we would have to create a so-called source using a seed, and that's a little bit too advanced right now. I'll attach an article that dives a bit deeper into that if you're interested in it. For the moment, I'm fine with getting the same random numbers, which is not really random, but you get my point, because this section, of course, is all about writing and using custom functions, and that works quite well now also with multiple return values. Now, when working with return values, no matter if it's one or multiple return values, you can use a little shortcut in Go, which I only recommend for usage in simple short functions, since it can make your functions a bit harder to read if they get very complex. You can name your return values. And at the moment, we're not doing that. In both functions where we have return values, we just define the type here, and then we return values like this. And that's the default case, which I recommend for most functions. But for simple functions, we could also work with named return values. To do that, we have to wrap our return types into parentheses, even if it's just one. And now we can use any name of our choice for that return value. For example, sum. Now that creates a brand new variable, which is available inside of this function, which is declared right from the start, and which is initialized to the null value of that type. In case of an integer, sum is initialized to the number 0. And then here in the function, we could use that variable, which is now available, to store that result, for example. Now here I don't use colon equal sign, but just equal sign, because the variable already exists. As I just mentioned, it's created automatically by Go. So I just assign a new value to it, effectively overriding its null value, the 0 value, and then that's the new value stored in sum. And now we don't even have to return sum, though we can do that as well, but it is enough to just call return, and Go will then automatically return the variables defined here in that return list. So it will return sum here. Hence, if I save that all, and I now run this again, this still works just fine as it did before, but now with that slightly changed syntax using these named return values. And we can do the same if we have multiple return values. For example, here we could use R1 for the first random number and R2 for the second random number. And then here we just set new values to these variables. Hence we have to remove the colons because the variables already exist. And then just calling return is enough. And here this certainly saved us a bit of code. It's now shorter and maybe a bit more readable. So in short, simple functions, you might be able to simplify them by using named return values. In very long, complex functions, where you then maybe also introduce other variables throughout the function, which will not be returned, it can quickly get confusing. if you use named return variables and this return statement, which doesn't directly clarify what it returns. You then always have to have a look at this list to understand what's returned. So it's a trade-off, but it is a feature worth knowing since you will see it in other Go examples in the built-in Go packages and also from time to time throughout this course, like with these examples here. And that's it for functions. It is a rather straightforward feature, nonetheless a key feature which you'll use all the time to split your code into reusable code blocks, which you then can execute when you need to execute some code, potentially also multiple times. You can call every function more than once if you need to. And you learned about all these key features that make up functions. How you generally define them with the func keyword, that the name should describe what the function does, with exception of the main function, which is a special function, that you can but don't have to take input parameters, as many as you need, separated by commas, where you give them any names you want and define the value types they will be of, and that you can return values, but you don't have to do it. If you return values, you have to define the type right after the function name and parameter list. And you can optionally also use these named return values I introduced in the last lecture. You can also return multiple values in one function, in one and the same line. And you can then, of course, also store these multiple values in variables and then do with them whatever you need to do. These are functions, and now to practice them a bit more, we'll go back to the body mass calculator and see how we can improve our code there by using functions, more custom functions. We learned about functions, now it's time to again apply what we learned. And for this, we'll revisit this BMI calculator we worked on earlier in this course, and we'll again apply what we learned to break up the code we have in this BMI calculator and split it into multiple functions. So that in this module, we do practice how we can write custom functions by splitting up that big main function which we got at the moment. And whilst doing that, we'll also see an example for how functions help us reuse code and why we use functions in the first place. Now for that, we'll continue working on that BMI calculator code we worked on before in this course. And in case you skipped that module or you don't have the code at hand right now, attached you find my code snapshot with that project as we left it. And of course, I want to say it right away, this project could stay the way it is. It works just fine, but of course we have a rather big main function, though of course it depends on how you define big. But this main function does multiple things. And as a general rule of thumb, you want to try to write functions that only do one thing each. I do have a complete course about writing clean code, which applies to basically all programming languages, and I do talk about that there as well. And this function, this main function at the moment does not do one thing, but it does all the things we do in this application overall. It prints some information here, then it gathers the weight and the height inputs, it does conversions, or it cleans the input and then does conversions, and then it does the actual BMI calculation. And therefore here we can certainly split up that function into multiple smaller functions to split that workload. Now, definitely feel free to try doing this on your own first. Come up with a couple of functions you could write on your own, and then move the different functionality into those different functions and make sure you glue them together in that main function again then, possibly using parameters and return values where needed. You can even try to split your custom functions across multiple packages, but that's totally optional. Now, in the next lectures, we're going to split that up into multiple functions together, and then you can always compare your solution and your approach to mine to see how I solved this. Now, to split that up into multiple functions, let's first of all identify the different workloads we have here to find out what we might want to split up. And we could, for example, put this general information into one function that we call. Then we could put the logic for fetching weight and height into separate functions. We could even put that logic for reading user input in general into a custom function. And we might want to put that cleaning and parsing step into a separate function. And then, of course, we also might want to put this BMI calculation into a separate function so that if the formula would change, which it of course won't, but if it would change, or if we would change the code somehow, and we would be calculating the BMI in different places of our application, we only have to change it once instead of having to search through all our code base and changing the formula in different places. And then last but not least, of course, this output here could also go into a separate function. And therefore, I'll start here at the very top with outputting that information. For that, I'll add a brand new function. And since we already have a separate package called info, I'll put that function into that package. Not something which you have to do, but something which might make sense given the fact that we have that package already. So in this info.go file, I'll add a new function, which I will name print welcome with a capital P at the beginning, because this function should be callable from outside this package, so from inside other packages that import this package. And it won't take any parameters, it doesn't need any input, and it also won't return anything. But instead, inside of this function, I just want to use the format package. Hence, we have to import format here in this info.go file. And then here, execute the println function, which is built into that format package. And print the main title, which we now actually can convert back to a lowercase m at the beginning, since we only use it inside of this info package. Will not use it in other files anymore in the near future. So here I'll refer to main title with a lowercase m. And then I'll also print my separator, which now also can be transformed to start with a lowercase s, since I'll only use it here in this package. I'll keep weight prompt and height prompt the way they are, since at the moment they are getting used outside of this package as well, and hence I only added this function and changed these two constants. Now back in bmi.go, instead of having these two lines of code here, we can use our info package, which we are already importing here, to call that print welcome function like that. So we still call a function like this if it's from another package. The only difference is that we refer to that package and then use this dot notation to access the function in that package which we want to execute. And that's step number 1. That's my first custom function using what we learned before. As a next step, we might want to gather the weight and height inputs. And for that, I'll add another new function, maybe in that same file or in a different file. The input.go file might be a suitable file given its name, which is part of the main package though, and that's fine. We could also turn it into a separate package, but I'll keep it as part of the main package. And in there, I'll add a new function, which I'll name getUserMetrics. Again, the name is up to you, but you should describe what the function does, and this function should deal with fetching the user weight and height inputs. So that should be a good name. And for this function, I don't expect any parameters, but we'll have return values, and actually we'll have more than one return value. We'll have a weight and a height. So we will return two values, and therefore we have to specify those return values here, or their types to be precise. You learned that if it's more than one return value, We have to wrap the list of return value types in parentheses here, and that's therefore what I'll add. And then we have our curly braces with the function body. But which return value types will we have in getUserMetrics now? Well, that is up to you. We could return the fetched weight input and height input strings, and then continue with cleaning them and so on in the next steps in the main function. Or we could argue that actually the getUserMetrics function should already do the cleaning for us and should therefore return the floats in the end. And that argument would make sense to me, that getUserMetrics should return floats and not just the raw user input. And therefore I'll return two float 64 values here. And then inside of getUserMetrics, I'll execute this code here. So I'll cut that code from bmi.go and add it here in input.go. But of course, for that to work, we need to make sure that we again import format and info here. So I'll click on format, go to the light bulb and add the format import, and do the same for info. So that's now also imported. Now I then get my weight and height input, and then I can return those values, though we first of all have to clean them. So we can go back to bmi.go, remove those comments, and grab those lines of code where we clean the input and parse the float from the input text, and cut that from bmi.go as well, and go back to input.go and add it here in getUserMetrics. And then here we do all that cleaning and parsing, and we should therefore import those packages, strings and strconf, like that. And then ultimately at the end, here at the bottom, we can return weight and height like this. Alternatively, we could work with named return values and name this weight and height here when we define the return value types, like this. And then we don't create new variables here, but instead we assign to existing variables like this. And we can just call return like this and automatically the named return values, so these two variables, will be returned. Both works, and it's up to you which approach you prefer. Now with that, back in bmi.go, we just have to call getUserMetrics. We don't need to import that from a package or call that on a package, since it's part of the same main package here. So just calling it like this is fine, and starting with a lowercase character is fine since it's the same package. And then we just have to create weight and height here and store the returned values in those variables. Whoops, like that. And here we need the := operator, because here in the main function we are creating brand new variables. We didn't have those variables before. And with this, if we save that, imports should get cleaned up automatically as soon as we save. We can try running this again, and it should still work fine. And it does. But now we added a couple of custom functions. Still, we can do more. We definitely did split up our code quite a bit, but still we're doing more than one thing in main. We have different levels of abstraction here, as it's called. We're calling some functions, and then we're all of a sudden doing some low-level calculations. We typically want to avoid that. And in input.go, that getUserMetrics function is also still rather big. We could make an argument for breaking that up even more as well. And I want to do both. Make bmi.go simpler and break up the getUserMetrics function more. Now I'll start with bmi.go. And first of all, I want to outsource this formula. Here I'll create a function in the same file, since it makes sense to have the formula for calculating the body mass index in the file called bmi.go, I would say. So here I'll add a new func and name it calculate BMI, because that's what we're doing. And I expect to get two input values here, weight and height. We need that in order to derive the body mass index. So here I'll add weight and height as parameters. The names are up to you though. They don't have to match the variable names up there because we won't have access to those variables in this function anyways. So these names are really totally up to you. But weight and height describe pretty well what will be stored in there. And we definitely do have to define the value types of those parameters. And here I expect to get float 64 values, so I'll add those type names after the parameter names. And then we can grab that formula, cut it, and instead just return it here. Using weight and height, like this, and making it clear that calculate BMI will return a float 64 therefore by adding float 64 as a return value type after the function name and parameter list. Now here back in main, we can just call calculate BMI and pass in weight and height like that. And now I'll also remove the comments to make this all a bit more concise and shorter. So now we outsourced this into this function, and the advantage, as mentioned before, would be that if we would call calculate BMI in different parts of the application, and we ever want to change this formula, we only have to do it once inside of that function definition instead of having to go into different places in our code and adjusting the formula in all those places manually. This can save you a lot of time as your application grows. Now, as a next step, I also want to outsource this line of code here, line 16, and put that into a separate function. We could do that here in the bmi.go file, but where calculate BMI made a lot of sense to reside in a file named bmi.go, just printing some output could possibly also go into another file. Though of course we could also add the function here. You can always have a discussion about that, and it always comes down to personal preferences. But since we have an input.go file, I'll also add an output.go file here, which should be responsible for outputting the results of our calculation. And I'll add that to the main package as well. But in there, I'll add my function called print BMI. And I expect to get the BMI as a input, as a parameter, and it should be of type float64. And then that code, which we have in bmi.go, this line of code will be extracted from there, will be removed from the main function, and instead will be added into this print BMI function. Here we now just again have to add the import of the format package. And with that back in bmi.go, here in the main function, we can just call print BMI and pass our BMI to it. If we now save that code, the format import gets removed there because we're not using the format package anymore in this bmi.go file. And we now have a very lean bmi.go file in general. Only 19 lines of code, and that includes all those blank lines which are added for readability. That's not too bad. And with that, I'm quite happy with the bmi.go file. I'm happy with output.go, but I definitely want to revisit input.go and talk about get user metrics. Because whilst we also could leave this function as it is, it's definitely not super complex, we could also argue that this should be split up as well. And that's therefore the last thing I want to do in this course section, to dive even deeper into functions and gain more practice working with functions. In input.go, this getUserMetrics function could be split up into a function that fetches the weight input, one function that fetches height input, one function that cleans weight, one function that cleans height, and so on. But splitting this into 6 different functions or more does really not make too much sense to me. Instead, I would say it's quite interesting to think about what this function does in other terms. Instead of thinking about the steps fetching, cleaning, and parsing, we could also think about weight and height. So we could say that cleaning and parsing weight is all one step combined with getting that input in the first place. And the same is true for the height. Now we only have two steps here, which we could outsource into separate functions. And if we take a close look at that code here, we have a prime example for creating a function that can be reused. Because in the end, we perform exactly the same operations twice. And having code duplication as we have it here is never a good idea. You always want to avoid it so that you write less code and you have less code that you need to maintain. Therefore, I'll add another function in here in this input.go file, which I will name getUserInput. Now, this function should in the end perform all these steps. So I'll copy that and add that here. But of course, we now need more generic names. Because now, for example, it's not the weight input, it's the user input in general. Because we'll use that same function for getting both the weight and the height. So here I'll not name this weight input, but just user input instead. And of course also here and here and here. And therefore that here is not the weight, but instead just the entered value or anything like that. Whatever name makes sense to you. And that's what I ultimately want to return here, the entered value. Now, of course, here I am always printing that weight prompt though. So that's still weight specific and not very generic. To make it more generic, we could accept this prompt text as a parameter of type string and just output that here. So output this prompt text here with print. Now we get that from outside when that function is called. Then we perform the same steps no matter if it's about the weight or height, which makes sense because we parse the values and clean the values in exactly the same way. And then we return the entered value. And since we return a value, we should also specify the return type here, and that's of course float64. And here I now also should create entered value and add my colon here, therefore, so that this entered value variable is created. Alternatively, of course, we use named return values by wrapping this into parentheses and giving this a name of entered value, or maybe even just value, and then removing the colon here and referring just to value here, and remove it here in that return statement line. That will do the same thing. It will parse that float in the end and store it in this value variable, which is declared right at the start, initialized to its null value, which in case of a float is 0.0, and then we'll override it with that parsed float value and return that value ultimately. And now we can use that getUserInput function here instead of having these large code blocks twice. Here we can get rid of that, and instead we just get our weight here by calling getUserInput, and to getUserInput I'll pass info.waitPrompt so that we show the appropriate prompt text. We expect that input parameter here in getUserInput, hence I pass it in. And waitPrompt is a string, this constant string specifically, and hence we fulfill the requirement of passing in a string. Then we get back a float, and since we prompt for the weight first, we know that this will be our weight. Well, and then we can just copy that and repeat this for the height and store that value and use the height prompt here. And now we can get rid of that code as well, and then just return those values. And that's now a better approach, I would say, And it's a good example for why we use functions in the first place. If we ever change our parsing or cleaning logic or how we read user input, if we want to react to a different character than the enter key being pressed, we only need to do it once here in this getUserInput function, and it will then change for both places where we call that function. Because here we are using the big advantage of functions, which is that we can call functions multiple times with different inputs and getting back different results. And as a developer, you should always strive for solutions like this, where you have as little code duplication as possible, since that will make your code easier to maintain and it will make it easier for you as a developer to change your code. And that's it for this section. You could definitely come up with more ideas of splitting this up into functions, either splitting it differently or maybe even splitting this into more functions. But you definitely don't want to reach the point where you put every line of code into a separate function. That's not the idea. Nonetheless, you saw some advantages of functions in this section, like here, the removed code duplication. And in general, we now practiced in detail how we can work with functions, with function parameters and return values, including named return values, and how we deal with functions in general. I can only encourage you to play around with that even more, build your own other demo projects, or dive deeper into this project and maybe put some functions into separate packages, or come up with different ways of splitting up those functions. For the moment, we are done with this though, and we're ready to move on and now dive into more exciting Go features. Up to this point in the course, we had a detailed look at a lot of basic concepts. Now we're going to get a bit more advanced, because in this course section, we are going to dive into a concept called pointers. And I'll explain what exactly pointers are and why we have that concept. And I will then also show how we do work with pointers. Because pointers will be very important in later course sections and in even more advanced Go concepts, and therefore it is important to get them out of the way right now and to get a first introduction into this pointers concept. Now, to answer the question what pointers are and why we have them, we first of all need to take a step back. We need to look at how data, values that we work with in our code are being stored. And here, an important thing to notice and keep in mind is that values, so strings, integers, floats, and so on, are stored in memory, in your computer memory. And that's true both for values which we store in variables as well as values which we only use once. So for example, if we create a string in the println function call and we don't store that string in any variable. We only use it once, but still, this is a value, this string is a value, and it is being stored in memory therefore. Now there is a difference between those two cases though. On the left side, if we store a value in a variable, then it's kept around in memory until we don't use that variable anymore. And Go will detect if there is no more code left to execute that doesn't use the variable anymore. And on the right side, of course, we instantly don't need that value anymore. So it's used once, and thereafter Go realizes that this value won't be needed again. And for such unneeded values, which will not be used again in the code, there is a built-in mechanism in Go, which is called the garbage collector, which is a little process automatically executed by Go, which will look for unused values and remove them from memory to free up memory. so that if you have bigger programs that are being executed, you don't slowly run out of memory and you take up a lot of computer memory, but that instead unused values are erased from memory. Now, all of that is taken care of by Go for you. You don't need to actively manage the memory, but you should understand that values are being stored in memory, because that will then also be important for understanding pointers. And for that, to move a bit closer towards understanding pointers, let's take a closer look at what storing in memory actually means. How are values stored in memory? For this, we have two sides. We have our values and possibly the variables that hold those values, and then we have that computer memory. Now you can think of that computer memory as a big space with different storage slots, which each have addresses. Basically, just as you have a couple of buildings in a village or a city, and every building has a clearly defined address, typically made up of the street, the specific number of that building in the street, maybe a postal code, and so on. These are addresses of buildings in a city, and it's the same for computer memory. You have various slots, and every slot has an address. That's how you can think about that. Now, if you then create values, for example, because you store them in variables, but also if you would not store them in variables, so if you would use them only once, as you saw it before, then those values get stored in memory. So every value gets its slot in memory, and what you see here on the right in those boxes are those addresses the computer knows for those storage slots. So now in these storage slots, the values from the left, max and 32, are stored, and these storage slots then each have a unique address, which of course is important to retrieve the stored values. Of course, you can also have storage slots that are not occupied, so you can have empty storage. And typically you will have empty storage because if there is no more empty storage available, you're running out of memory, and that typically means that your computer crashes. Now in your code, if you store values in variables, the variables know about these addresses. And whenever you then work with a variable somewhere in your code, for example in a calculation, Go will automatically take that address information and get that value for you. So it's fair to say that we store values in variables because whenever you work with those variables, you will get the values automatically. That's how that works behind the scenes. Now, if we move towards pointers, we still have that idea of storing values in memory and having addresses, but now we have this new concept, pointers. And pointers are in the end just variables that do not store the value itself, but only the address. So they don't go to memory and get the value for you whenever you use them in a calculation, but instead they only store the address and nothing else. The syntax for creating a pointer looks something like that, but we'll see this in action in a second. And in the end, what happens here is that user age will be a pointer, and it looks at age and gets the address of the value stored in age, and then user age only contains that address. And if you would use user age in any calculations, you would not get the value automatically. Instead, you would only get the address. Now, that's the idea behind pointers, and we'll see them in action and write some code very soon. But one very important question that probably came to your mind now is, why do we have pointers? What's the idea behind them? Which advantages do they offer to us? And indeed, pointers do offer various potential advantages over plain values, though I will say right away that it's specific use cases where pointers are important. There's nothing wrong with plain value variables as we use them up to this point in the course. But pointers can offer us various advantages. For example, we can pass them as parameter values to functions, and then if we do that, since we pass the address of a value instead of the value itself, once the function executes, Go does not have to create a copy of the received value, so of the parameter value, but instead it can just use the address itself, and you can use that inside of the function to then get the value from that address. Might sound a bit cryptic right now, but we'll see it in action in this section. Another example, also related to functions, would be that we can pass a pointer to directly manipulate a value stored somewhere in memory from inside the function, so that we don't have to return a value and then store that in the place where the function was called, but we directly manipulate some input value from inside the function. And that can also sometimes be useful. And there are other advantages, but that will become clearer once we dive into other, more advanced concepts in this course. For the moment, let's just get started with the core pointer syntax and play around with them a little bit to understand them a bit better, and then in the next course sections we'll also build up on this knowledge, since then we'll use more and more pointers for specific use cases and problems. Now I am back here in an empty project, and again I'll start by creating a new Go module with the go mod init command. And again I'll use this sudo github address I used before as a module name, and use pointers as a module identifier in the end here. Hit enter, and that now created that go mod file. Now I'll add a pointers.go file in here, and in that file I want to write some pointers related code. For that, of course, we start by still making that our main package, and we still add that main function. We always need to add that if we plan on executing this file. And now in here, let's see how pointers work. For this, I'll start by adding a simple variable, age, which holds a value, 32. And then I'll use the format package, and hence, of course, we need that import to print ln this value, this age value, as we did it many times before. Now, of course, should be needless to say, if we now run this here, if I go run this module, we get 32 in the terminal. Now here, I'll add a pointer. And I'll name it my age by again using that colon equals syntax, since I haven't created that variable before. So I want to create it here in this line, and therefore we still use this syntax. But now I use age, but not like this, but instead we add the ampersand symbol in front of age. That's a special symbol which is picked up by Go, which tells Go to get the address of the value stored in this variable, so of this age variable. And hence, if we now again print something, but this time we print my age, then you see I don't get an error here. But if we open that terminal and run this code, now we get 32 from that first print statement still, but from this second print statement where I print my age, we get this strange value. And that, of course, looks similar to the values you saw on the slides before. This is the address of the value 32 in memory, because my age is a pointer. And if we hover over it, we see that a pointer type is reflected like this by Go. It's basically an integer, but this asterisk in front of it means that it's a pointer at an integer value. So it's pointing at a place in memory where some integer is stored. That's what this asterisk means. And if you would not use this shortcut here for creating that pointer variable and initializing it in the same step, but you instead would want to do this manually, the syntax for that would look like this. You create a variable myAge, and the type now is asterisk int. And then in a second line or in the same line, you could still assign a value as we did it before. By the way, if you remove the ampersand here, we would get an error Because we here in line 11 say that my age should hold a pointer at an integer value in memory, whereas in line 12 we would then assign the integer value itself, not the address of that value. And that's invalid. We can't use an integer value in a place where the address of an integer value is expected. And the ampersand symbol here tells Go to go and pick up that address of that value in that variable. So that's how we can create a pointer and work with a pointer. And here I'm getting yellow squiggly lines because I have this unnecessarily complex declaration and initialization code. But I wanted to show this as well to make it very clear how this pointer type looks like. And of course, we don't just have asterisk int, we can also have a pointer at a string value or a float 64 or float 32 value or a rune, and then we would have asterisk string and asterisk rune and so on. But here we happen to point at an integer, so it's asterisk int. However, with that, I'll comment this out and go back to this slightly more concise syntax. So now we have such a pointer. What can we do with it? Well, for example, we can use it to still get the value at which the pointer is pointing. Keep in mind, here in line 14, I'm printing the pointer, and if we run this module, we therefore get the address, because I'm printing the value stored in this variable, and that value is the address of age. Hence, we get the address here. But if I want to print the stored value instead, we can get access to that again with the address here by adding an asterisk in front of this variable. We saw that asterisk before on the type when we created the variable. We can also use it in our code if we have an address and we want to get the value stored in that address. So we have ampersand to get the address of a value, and we have asterisk to get the value stored in an address. So basically to reverse that operation. And therefore now if I save this with the asterisk added here in line 14, if we run this code again, we now get 32 here because we do now get access to the stored value. This process, by the way, is called dereferencing, because we're diving into that address and getting that value. We can also not just read values with help of pointers, we can also assign values. So for example here, we could use myAge and store a new value in it. Now here you have to be careful. If you try to do something like that, you will get an error if you want to store 33 in myAge. Why? Because myAge is a pointer. It's not the value itself, it's the address of the value. So in myAge, we are only allowed to store addresses. Now 33 is not an address, it's probably the new value we want to store in that address. But then we can't assign it to a variable that only contains the address. And that's basically the error we get here. We can't store that integer in a place where the address of an integer is expected. As a side note, in other programming languages like C++, for example, you can do something like that, and you can then change the address stored in a pointer like that, but that can also often lead to problems where you accidentally change some address. It can also lead to security issues, and therefore Go does not allow that. But how could we now change the value stored in that address? For this, we again need to dereference our pointer. We can again add an asterisk here, and if we do that, we tell Go that we want to change the value stored in the address stored in myAge. And we want to set the value stored in that address to 33. And therefore, if we then print myAge thereafter again, and I don't mean myAge itself, but we dereference it and we print the value stored in myAge, then if I again run this module, we print 33 here in the end because we changed the value here. By the way, what do you think would happen if we don't just print the dereferenced myAge, but we print age itself? So the variable which we created here at the very beginning. What do you think do we get if we print age here at the bottom of the main function? Well, let's give it a try. If I run this module, we get 33 as well here. And that shouldn't come as a surprise because we're working on one and the same value. We created the variable age, then we got the address of that variable, of that value stored in the variable to be precise, and we stored that address in my age. And then we used that address to assign a new value to it, so to overwrite the value currently stored in it. And therefore, of course, age now also has that new value, because age and my age in the end are referring to the same value in memory. The only difference is that my age only holds the address, and we explicitly need to reach out to the value with help of the asterisk. Whereas age does also know the address, but automatically works with and on the value whenever we use that variable. So here we don't need to explicitly reach out to the value when we work with age. But we are working on the same value stored in the same address in memory in the end. And that's how pointers work. But of course, with this very basic example here, it's still not really clear why we might want to use pointers. After all, pointers are just a bit more complex to work with. We always have to add that asterisk, and there isn't a clear advantage of using pointers, right? Well, this was just an example to understand the general syntax. Now I want to show you what you can do with pointers and with that concept of having the address instead of the value. So let's explore why we might want to use pointers, though I want to say right away that the real good use cases will come a little bit later once we also learned about other important Go features. Nonetheless, let's see an example here right now. Let's say we have a function called double here, which takes a number as an input, as a parameter, which is an integer, and which should return an integer. And in that function, we might just return number times 2, which will double the input number. Then, of course, here in my main function, I could create a doubled age variable by calling double and passing age, so not the pointer, but the age variable itself, which stores the value itself, to double. And then thereafter, we can, of course, print doubled age like that. Okay, if we do that, it should not be too surprising that if we run this file, we get 66 as our output in the end, which is simply our current age, 33, before this line times 2. Now, what happens here, if we have a function like this that takes a parameter, is that whenever this function is called and a value is passed as a parameter value, like age here, Go will go ahead and copy that value. So it will create a new entry in memory and store that value in that new entry. So if we before had one place in memory where the age was stored, we now have two places. One for the original age and one for the new age. And we can tell that this is the case if we add a result variable here, in which we store number times 2. And then after doing that, we set number equal to 100. And then here I only return result. If I do that and the number would not be copied, so we would get the address of age and we would work on that same value inside of this function as we work on in the main function, then changing number to 100 should actually ensure that the number we pass in is 100 after we called this function. So if I print my age thereafter, this should be 100 if Go would not create a copy of age inside of this function. So if you would operate on the same value in memory, then age should be 100 here, because we override it here inside of the function. But as you can probably already tell by the way I am phrasing this, if we run this module, we get 33, not 100. because Go is creating a copy. And it has good reasons for doing that, because this ensures that inside of a function, we can't accidentally change a value defined in some other place of our code. If we call the double function and we pass age to it, we can't accidentally change age from inside this function. We only change the local copy of the provided value, and the original value is not stored. Now, that extra place in memory that is occupied is of course freed up once the function execution finishes, because then this number variable is not being used anymore, because it only exists inside of this function. So then it can be garbage collected. But still, during that function execution, we have that copy. And this is not bad. As I just explained, it is a behavior that makes sense. Now, for numbers, this will also probably never be a problem. But we will soon learn about more complex data structures beyond numbers and strings. More complex data structures that can take up more space in memory. And if such data structures are then copied, we have two big data structures in memory. And depending on the kind of application you're building, that could then actually lead to a lot of memory being occupied just because you're calling a lot of functions. And that can make your program slower. Again, definitely not the case here for a simple number, but for more complex data structures, that is a problem into which we can run. And now that is a scenario where pointers could help us. If in double, we don't expect the value, but instead a pointer at a value, so we expect an address, then Go won't copy that value. So here we can make it clear that we want a pointer by again adding this asterisk in front of the type. Now double wants a pointer at a value instead of the value itself. So when we call double, we no longer can pass in age, which holds the value itself, but we should pass in my age, which holds the address. So which is that pointer? And my age like this, not with an asterisk in front of it, because we don't want to pass in the value, but really the address itself. So that here we get the address of a number in the end. Now, we shouldn't change it, of course, here, and we can't change it, so let's get rid of that dummy line. And we, of course, now also need to dereference it if we want to work with the value. So here, when we derive the result, we need to add an asterisk in front of number to get the actual value stored in that address, so that we can then perform this operation on that value. But now, whenever we call double, we'll not copy that value in memory and occupy new space in memory. Instead, we'll just pass the address into that function, and then in here we work on the same value as we have it here in the main function. And therefore, if that would be a more complex data structure, we avoid that possibly very expensive, from a memory perspective, this very expensive duplication. Now, if we save this and we run this program again, we get the same results as before, but we have this possible performance gain. Now, that was one of the two advantages, or potential advantages, of pointers. Another advantage could be that we can now edit the original value from inside a function. Before, this was not possible because we got a brand new copy. And as we saw a couple of minutes ago, if we tried to change that, if we tried to change it to 100, that had no effect on the original value. Well, now, since we get the address, we can, of course, change the original value. Here, I could now reach out to the value stored in number by adding the asterisk at the beginning and set this to 100. If we do this and we now run this module again, we get 100 here at the very bottom for this print line statement here, because we did change the original value because we got its address here. And through that address, we can access that original value from inside this function. Now, sometimes this can lead to horrible bugs and you want to avoid it. But sometimes you also have functions that should indeed manipulate the original value. Again, it's most useful if you have more complex data structures which you might want to manipulate from inside functions. This here, of course, is just a dummy example which has no real purpose. But with that, you still hopefully get an idea of what pointers are and what you can do with them. Now, throughout the rest of the course, where we will now explore more advanced features and more complex data structures, it will also become more obvious when and why you might want to use pointers. You definitely don't need them if you only work with simple integers or strings, as we're doing it here. But now we got the foundation to dive in deeper. We explored pointers, and I mentioned that they would be most useful once we also dive into more complex data types. Well, in this course section, we are going to dive into such data types where we then also see reasons or situations where pointers can be helpful. We are going to dive into the struct data type, and we're going to learn how this struct thing helps us structure our data and when we might want to use it. And for that, in this course section, we're going to learn what exactly a struct is and why we might want to use it. And of course, we're going to see it in action with some dummy code before we then in the next course section also use the struct concept or the struct structure in a more realistic project again. Now for this course section, I prepared a little starting project which you find attached. It's one file mainly, and then this module file. And in this structs go file here, you find a bunch of code which generally only does things we already saw before. I got a main function, I got a reader, and in the main function I'm calling the getUserData function, which is this function here, where I gather some user input from the command line so that I can then enter a first name, a last name, and a birth date. Then here I create a time snapshot. I get the current timestamp by using the now function provided by the built-in time package. Then we might be doing more awesome things. It's of course just a simple dummy example, so we're not doing anything here, but it would be realistic that we are building an app where we are fetching some user data and where we then do more amazing things with that data. Here I'm just printing it to the command prompt so that we see that all of that works correctly. And therefore, if you download this and create your own Go module with the go mod init command, giving it a unique identifier, you can then run this module, and in the command prompt, you are then prompted to enter your first name, your last name, and then also your birth date. And here I'm coming up with some date. This is not my actual birth date. And if I hit enter, then this is all being output down there, as you see, and therefore this application overall works. Now here we're not doing anything new besides this timestamp. The rest of that code is all code we saw before. But there is something special about this example and this simple use case, something which you will encounter in a lot of applications you'll be building. We have some data, first name, last name, birth date, and the created timestamp that actually kind of belongs together. Nonetheless, here I'm managing that data in 4 separate variables. And that's of course not wrong, but if you think about more complex applications where you might be dealing with users and maybe products and maybe orders if you're building an online shop, then you often have packages of data, you could say, where multiple pieces of data are grouped together. For example, this data here could describe a user of our application. And very often you might want to pass that data around in a package, so that if we had some other function that is responsible for outputting user data or for storing data in a database, we can pass the entire user data package to that function instead of having to pass individual variables. So the data types we learned about thus far are not enough. Strings and integers and floats and so on are all great for simple pieces of data, but if we then want to combine that data and describe a more complex entity like a user, then these data types do not suffice. And that's why Go has a special data type that we can use to group data together, the struct data type. And we have similar concepts in other programming languages. In JavaScript and Python and many other languages, we have so-called objects. And the struct is basically Go's equivalent to those objects, in case you did work with other languages before. Now, in Go, in our Go file, outside of the function, just in the file like this, we can define our own data type, our own struct, by using the built-in type keyword. This tells Go that we want to define our own data type because the built-in types are not enough. Then we can give this type any name of our choice, for example, user. But that name is up to you. And again, you can start with an uppercase character if that type should then also be available outside of this package, in case you split your project in multiple packages or you distribute it as a third-party module. And you can start with a lowercase character if that should be a type that's only usable inside of this package. So just as you learned it about variables and functions, the same thing applies to this custom type. Now here I'll go for an uppercase character, because here it doesn't really matter to me whether that's available outside of this package or not. And then we need to add the struct keyword. With that, we are telling Go that we want to define our own type, and that this type should be a struct thing, a structure, so to say, an object in other programming languages. Then we add curly braces, opening and closing, and between those curly braces, we can now describe our own data type. Because keep in mind, the idea behind the struct is that we group together related data. Now, between those curly braces, we can simply define the different data fields that we want to have in this struct. And here you can come up with any names for these fields you want. Like, for example, a first name. A user should have a first name, we could say. So here we then just add first name, just as if we would be defining a variable, but without the var keyword. And then you need to define the type of data that should be stored in that field. And here that could be a string. And that's how you now define a user that will have a first name field, which is of type string. And if we later want to create such a user struct in our code, so if we want to use this blueprint, so to say, to create a concrete instance of that blueprint, we will be able to assign data to that field. And of course, you can also add more than one field. You can also add a last name, which is of type string, and then maybe a birth date, which is of type string. And the names I'm choosing here happen to be the same names as I have them down there for the variables, but you don't need to use the same names. You can use totally different names here. You don't need to pick up those variable names. But now I got that. I'll also add a created date here. And here the type will actually be a special type. The type will be time.time. And that's a strange type which we haven't seen before, but this is actually just a custom type defined by Go. If you hover over it, you see it's a struct, but not a struct defined by us, but instead, this is coming from the time package, which is built into Go, so it's a struct defined by the Go developers. So besides integers, strings, floats, and so on, so beside these basic types, we can also define our own more complex types, and there also are a bunch of predefined more complex types that are part of some of the Go packages, like this time struct type that was defined by the Go developers. And now with that, we're saying that we will have our own data structure called user, which will have these data fields. And we can now also use this as a custom type. And therefore, in the main function here, we could now say that all that gathered data should be grouped together into such a user object, into such a user structure. For this, we could, for example, already define a variable here, default user or new user, for example. Name is up to you. And make it clear that the type of data that should be stored in this variable should be user. And of course, here I'm picking up my own type because, again, we can define our own types with that struct concept, and we can then, of course, also say that a certain variable should only be allowed to hold such kind of data pieces then. So here in new user, we can't store a string, we can't store an integer, instead we'll need to store such a struct. But how do we now use this struct blueprint here to then create a concrete instance of it here in our code once we got all that data? Here we gathered all the data. Here we defined that we want to have such a variable. Now we can go to new user and store a value in that variable. And then here create an instance of our struct by repeating the struct name, user, and then adding opening and closing curly braces thereafter. And between those curly braces, we now insert the data that should be stored in the struct. And we got two ways of doing that, to be precise. We can either repeat our field names like first name and then add a colon, but no equal sign, just a colon. And then after the colon, define the value that should be stored in that field. In this case, first name, this variable. So on the right side of the colon, I'm referring to the value that should be stored, and that's the value stored in this first name variable. On the left side of the colon, I'm referring to that field name where that data should be stored. And we can now repeat that. We can add a comma-separated list of all our fields here and also target the last name field and store the last name variable value like this. Target the birth date field and store the birth date variable value, a birth date written like this with a lowercase d because that's the notation I chose here, also to show the difference between left side and right side. And then we can add the created date field and store the created variable value in there. And that's how we can now create a concrete instance. Now, since this can get a bit hard to read, you can also split this code across multiple lines here. So you can also write this like that. And then hit the auto format shortcut. It's important that you have a comma after the last key value pair as well then, if you want to split this across multiple lines. And now we have a very readable way of creating a new instance of such a user data structure. And now that's what's stored in the new user variable. Now with that, instead of outputting all these individual pieces of data, we can refer to our new user variable now and try to output that. And that's what I'll try now. I'll save everything and then open up that terminal again, run this application again and enter some quick data like that. And we see that we get this kind of output here now. It's a bit different from what we saw before, especially that date thing here looks a bit different, but generally this is working and we are outputting our data, our new user data now. And the advantage is that we now have this data package, new user, which contains that grouped together data. And if we have a bigger application where we now also maybe have a function that saves user data to a database, we can just pass that entire new user struct to that function instead of passing the individual variables. And that, of course, can save us a lot of time, a lot of errors, and make code maintenance a lot easier in bigger applications. Now, there is more than one way of creating a concrete instance of our struct blueprint. And that's, by the way, important. We got the blueprint here, where we define our own type, and then we use that type to create a concrete instance of it. And that's what we're doing here. Now, there are a couple of ways of creating a concrete instance. Here we are using the struct literal way of doing it by using the struct name and then curly braces, and then adding those key value pairs of our fields and the values for those fields. There are also other ways of using that struct literal approach though. For example, if you plan on keeping the order which you define here, so first name, then last name, then birth date, and then created date, as I'm doing it here, then you can omit those key names here. You can remove all those key names here as long as you keep the order. So that is then also fine. And then we could also move it back into one line if that's easier to read for us. Here I'll keep it split out across multiple lines. And that's of course a bit shorter, so that's something you might want to consider. You can also omit all those values if you want to. Now I'm just getting an error here regarding those variables because I'm not using them anymore, but creating an instance of the struct like this is also fine, but of course it will be an empty instance. It will basically be a struct with all those fields, but all those fields are initialized to their default null values. So for example, to an empty string here. And therefore that's of course very often not useful, but sometimes it can also be useful to create it like that. Now you can also, if I go back to the approach from before, where I do include the key names, omit individual key value pairs. For example, now I removed last name, but I have all the other values and I'm setting all the other fields. Now all those fields will be set to those values I'm assigning, and last name will simply be set to the default null value, which is an empty string. So you got a lot of flexibility regarding that. What's also done very often is that you create a helper function for creating a struct, so that you outsource the logic of doing that here to another place in your code. That can especially be helpful if you have a more complex way of creating such a struct instance. And I want to show that to you as well. I'll add a new function and I'll add it right below the struct definition so that we always see that. And I'll name it new user. And this will be a function that's only responsible for creating new user struct instances. And the convention for naming that function then is that you have the word new in your function name and then the name of the struct that will be created, to make it clear that this is a function that will be responsible for creating new user structs. And here we could then, for example, say that we here expect to get the first name, and I'll just name it fname here, this parameter. It is of course up to you, that parameter name. That we get the L name, so the last name, and the B date for the birth date. I'm not getting the created date because I will now actually create that date inside of that new user function. So in that function, I now have my user variable, which I create here, and I use the user struct literal here to create a new instance of that struct. And I'll set first name to fname here, and I'll set last name to lname. And unsurprisingly, I'll set birth date to B date, like that. And I'll set created date equal to the current timestamp. And for that, I'll actually take that timestamp creation here from the main function and remove it from there, because we can argue that it is a process that's only related to the creation of a new user struct, since we only use the timestamp there. And hence I'll put it into this new user creation function here and get my current timestamp here and then use that variable here for storing that created date. And then of course here in new user, we can return this user struct variable here and make it clear that this function will return such a user by adding our struct type as a return value type for this function. And now we got this helper function which we can use from anywhere in our code if we want to create a new user struct instance so that we don't have to use that struct literal code in those places. So here in main, instead of using the struct literal notation here, I can now just call new user, so this function which we added, and then pass my first name, my last name, and my birth date to that function. And now we again will have a new user if I save that and if I would run this code. So that's yet another way of creating such a struct instance. Of course, we're still using the struct literal notation, but we outsourced it into a separate function, which also does some extra work. It gives us this timestamp, and we can conveniently call that function from anywhere in our main code whenever we need to create a new user struct instance. And of course, that's still our goal, keeping that main function and all our functions in general lean and focused on a specific task. And now we do have a function with the specific task of creating a new user instance. So now we know how we can define our own struct blueprint and how we can then use it in our code. Now I want to come back to pointers. Because in this code, which we wrote here, everything works, but it's not optimal. It's not optimal because when you call a function and you pass a value to a function, or if a function returns a value, that value is always copied. So for example, new user, this helper function, creates a new user struct and returns it. But what actually happens there is that a copy is created and returned. So actually 2 user objects are placed in memory. Now this one, which is created in new user, will be cleaned up relatively quickly because it's not required and used anymore once the function execution stops. But nonetheless, allocating and using 2 slots in memory just for the creation of 1 user object is simply not optimal. And structs are more complex than just strings and integers. They can store an unlimited amount of data in them. They can even store other structs in them. As we're doing it here, we're storing created date, which is another struct. As we see here, it is a struct defined by the Go team, and therefore copying such struct instances unnecessarily is something we typically want to avoid. Now to avoid it, we can use pointers. Instead of creating our user value here and hence copying it, we can return a pointer to the created user. That way we'll not duplicate it, but we'll only have it in memory once, and then we return a pointer to that place in memory so that other parts of our application can work with that stored user in that place in memory. And therefore here in new user, I want to return such a pointer. For this, we first of all need to annotate this return type and make it clear that we don't return the actual user struct, but a pointer to that value. And we do that by adding the asterisk here. That's what you learned in the pointers course section. By adding the asterisk in front of a type, you make it clear that you will not store a value of that type, but a pointer to such a value of that type. And then here, instead of returning the user struct, which is the value itself, we want to get the address of that user variable, so of that value in memory, and we learned that we get that address by using the ampersand symbol here. And now, new user creates a user, stores it in memory, and then returns a pointer to that value in memory. And now in the main function, we just need to tweak this line a little bit, because new user does now return a pointer. The new user variable, in which I want to store the returned value, expects a user value itself though, so not a pointer to a user value, but the value itself. Now to make that work, we got 2 ways. We either change new user to be a pointer, but then we'll have to adjust all the places in code where we use the new user variable, because now this is a pointer, not the value. Or we still want a value and we dereference the pointer which we get back here by adding a star in front of this. Dereferencing is the process of looking into that address, which we get returned by new user, getting the value, and then working with that value. In this case, storing that value in new user. Both is fine, and it simply depends on what your application does, whether you want a pointer to that user here in the main function or the user value itself. You can make either of the two approaches work. It really just comes down to what your application needs. And that is also something that will come over time with experience. Now let's build up on this struct and pointers knowledge. I'll add another function here, which I'll name output user details. Now this function should deal with a user struct. It should get a user struct, because that's the idea behind structs, that we can pass around the entire data packages. And here I want to get such a data package. And then I want to output some user data. So here I expect to get a user. You can name the parameter however you want, which is of type user. So our struct here. And then I just want to output this with the printf function here. And I'll just say my name is. Then I want to output the values of first name and last name. And I'll say in parentheses born on and output the date value here. That's my idea here. And then therefore here, the three parameter values which we need thereafter are the values that we want to output here in the same order as we referenced them here. And hence that would be the user first name, last name, and then also the birth date. But how does that work now? How do we get access to the individual pieces of data in the struct? We learned how we can output the entire struct. That's what we're doing in line 44. But how can we access the individual data pieces in cases like this, where we just need the first name and last name and birth date, but not the created date? Well, you work with a struct just as you work with a package in that case. You use the variable name that contains the struct, in this case this parameter, and then you use the dot notation. And with that dot notation, you then get access to those keys, to those fields that are stored inside of the struct. So for example here to the first name. And then separated by a comma for the next value that I want to output, the last name. And then another comma and the birth date. Now with this approach here, with line 48, we're outputting that user data in a more formatted way, and we now see how we can access the individual pieces of data that are stored in a struct. And you can also nest this in case you would need access to the created date, which is a struct itself as we saw. You can also add a dot on that struct, so on that date time struct here, which is provided by the time package. And also dive into some fields or even functions that belong to this struct, something we haven't learned about yet, with another dot here. So you can chain, as it's called, multiple structs after each other and dig deeper and deeper into such nested structs as well, in case you need to. But here we don't need to do that, hence I deleted that line again. We just want to output the user data like that. And now here, instead of outputting new user like this, we could call output user details and pass new user to it. Save everything and then open up that terminal again and run our module again. And now if I enter some data here real quick, we see that output works. But there is a flaw with the current approach. And do you see which flaw that is? Well, we are again passing our struct value by value, so we are creating an unnecessary copy. Here in output user details, we expect to get a user parameter which is of type user, so our struct. And then we pass new user as a value when we call that function. Now, new user is not a pointer because we dereference it here. It is the actual struct value. And therefore, as we learned, a copy will be created if we call a function and pass that value to that function. So now we again created a copy of that user. And sometimes that is what you want, sometimes you want a real copy, but often it's not because of that wasted memory. So therefore, in output user details, it would be better if we don't get the entire user value, but instead again the pointer to that value. And hence here, we can change this and add an asterisk in front of the user struct type here to make it clear that output user details wants a pointer to that user struct. Of course, we then have to pass in such a pointer here, and we get that by again using the ampersand. Or if that's the main thing we do here, we might not even dereference the pointer here, which we got from new user, and remove this asterisk, so that we have a pointer stored here in the new user variable, and we then just forward that pointer. Now we just need to make sure that new user, this variable, wants a pointer in the first place, and we do that by adding an asterisk here in front of the type. Now we want a pointer here, we get a pointer here, and we then pass a pointer to output user details. And with that, it again works. And if we save everything and then open the terminal again, we can run this again and still enter all that data here if we want to, and it works correctly. But maybe you can spot something in the code which is rather strange about that. It is actually a bit strange that everything worked just fine. And why could that be a bit strange? Well, here in output user details, we are expecting a pointer. And we are getting a pointer. We changed all the code such that a pointer is passed into this function. Nonetheless, in this output user details function, I'm then using the dot notation to dive into the different fields of my struct. But wait a second, user isn't the struct instance, it's a pointer to that instance. So user actually is a variable that just contains the address to the user struct, but just the address in the end. So we are using the dot notation on the address here, not on the actual struct value. So that shouldn't work normally. And it didn't work before in the previous course section when we worked with integers and strings and pointers. Well, here we're simply using a little shortcut Go is providing to us. Theoretically, you would have to, first of all, dereference the pointer by adding an asterisk, and then wrap this in parentheses so that you first dereference it and get the value, and then you use the dot notation on that dereferenced value. That would be the correct way of writing this. But since this is a bit cumbersome, and it's a very common scenario that you get a pointer to a struct, but you then want to access fields in that struct, Go gives you a shortcut and actually allows you to use the dot notation on a pointer to a struct, and behind the scenes it will then automatically dereference it for you. That's a little convenience that's built into Go when you work with structs and pointers, because as you probably recognized by now, it is quite common to combine pointers with structs to avoid the unnecessary memory cluttering. And that's why this works, even though it theoretically shouldn't work. Now, to conclude this section about structs, there's one last important feature about structs that we should not skip. And it's related to this output user details function. This is a function that's really tightly coupled to the user struct. It wants a user struct pointer as a parameter, and then we access the different pieces of data stored in the user struct. So this function doesn't work without a user struct. And that's of course different from getUserData, for example. Despite the name, this is a fairly generic function. It fetches some input from a user, but that can be any kind of input, and it could be stored anywhere, not necessarily in a user struct. So that is a fine function, but output user details, since it is tightly coupled to this user struct, can actually be turned in a different kind of function that is supported by Go. And that is a so-called method. Methods are still regular functions, but functions that are tied, connected to a specific struct. For this, I'll cut it. It's technically not required, it could stay where it is, but I'll move it up to my struct definition so that we have both close to each other so that we can immediately see all the things that make up that struct. And that's important because this function will now soon also be part of that struct or be an important addition to this struct. We can connect it, officially connected to this struct by changing this syntax a little bit. We can add a so-called receiver argument, which is a piece of syntax we haven't seen up to this point. Between the func keyword and the function name, we can add another pair of parentheses, and in those parentheses we can now define a single parameter that will point to a struct to which we want to connect this function. We could name it user and give it the type user. So just as we add parameters here in the main parameter list, but now in this special receiver arguments list here. Now we have a name clash, hence I'll remove user here in that main parameter list, though I want to emphasize that we still could accept other parameters if that function would need them, in addition to the struct. We can also still return a value if that would be required. It's still a regular function from that perspective, but it has this special receiver argument here. And this receiver argument is a Go feature that connects this function to the struct of which type the receiver argument is. So the receiver argument user is of type user struct, so this struct, hence this function is now connected. We can now also just name it output details because we already have that clear connection to the user struct because of this receiver argument. So repeating that in the function name is possible but redundant. Now this function can stay the way it is. The function body doesn't have to change, it still works as it did before. But we now call this function differently. Instead of calling it just like this as we did it before, we now instead call it on an instance of our struct. So we can use new user, which holds a pointer to this struct, and thanks to that shortcut which I mentioned in the previous lecture, we can use the dot notation on that, but now not just to access the different fields like first name and last name, but also to access this output details method. It's now listed here in this auto suggestion menu because of that receiver argument. So it's really an official thing supported by Go. So now we just call that function with that dot notation directly on new user, on the pointer or the concrete value, because of that shortcut mentioned in the previous lecture, both works. That's now how we call this function, which is tightly connected to that user struct because of that receiver argument. If we now save that code and we run this module, that still all works as it did before. It still works without issues because this is using this official method feature built into Go. And it's a great idea to turn functions that really only work with one specific struct into such methods, because you then have this clear coupling and you can use the dot notation to access that method on the struct for which you want to do something. So that is really a good feature which you should use whenever you have a function that is specific to a specific struct. Now in that method, I am using a user value at the moment, not a pointer. We can also expect a pointer instead by adding the asterisk here. Just as for the regular parameter list, both works and we have the same advantages and disadvantages. If we accept a pointer, we avoid unnecessary copying in the memory space, and therefore this is often the better choice. Of course, in cases where you want to create a copy, where you don't want to work on the original struct, you can instead also accept the value as we did it before. It again comes down to what your method does. Here, for just outputting some data, a pointer is definitely better because we avoid that extra copy, which would serve no purpose at all here. Hence, I accept a pointer here. And that's now how we can add such a method. A really useful feature for connecting a function to a struct if that function only works with that struct anyways. And that's also what we saw before on createDate, which is of type time, which is a struct built into the time package by the Go team. If we would access, let's say down here, new user createDate dot to dive into that time struct, we see a bunch of functions, methods as we know now, that are connected to createDate. So here the Go team defined a bunch of methods for the date struct that work with that struct only. For example, to return the day of the month of a specific date snapshot. So here we see that method feature in action for the built-in struct. Here we see how we can build it for our own structs with help of that receiver argument. Now that's it for this course section. We learned about another key feature, structs. Structs are great for defining your own pieces of data in cases where the built-in data types are not enough, or more specifically, for cases where you want to group certain pieces of data together. And you can group any kinds of data. Here we have a bunch of strings and another struct grouped into our own struct. So such nested structs, structs inside structs, are also possible. And then the great thing about such structs is that we can create them by using that literal notation here. And we can then pass around and work with those data packages instead of having to use all those variables over and over again in different parts of our application. Now, when it comes to creating structs, as I mentioned, we use that literal notation where we set all our key value pairs using the key names defined in our struct blueprint and then assigning fitting values. Or if we keep the order, so the order defined here, we could even omit those key names. So here I actually added them even though it's technically not required because I do have the same order of values as I expect them in my blueprint. So both approaches are possible. Here in this example, we also see another convenience feature which we can add to our applications, a creation function for our structs. It's a regular function in the end, but it does one main thing. It creates a new instance of that struct. It runs that struct literal code, and it even does some additional initialization work. In this case, it's creating this timestamp. Having creation functions like this saves us the hassle of running all that initialization code here over and over again in different places of our app. Of course, in this demo app, we only have one place where we do that, but in bigger apps, it would be very common to have different places where this happens, and then having such a creation function is very convenient. By the way, here where we call new reader on the buff.io package, we in the end also use such a built-in creation function, because it turns out that the reader which we get here is also a struct built into Go. That's just a side note though. Now we can then use structs to create them and store data in them, and we can also add methods on them, like output details which we added here. Thanks to this receiver argument, we can connect functions to structs so that those functions only work with those structs and are executed through the dot notation. And the dot notation is, in general, how we can dive into the data stored in structs. We can use it for calling methods, but also for diving into the different fields in case we need to work with that data, which is of course something we typically need to do at some point. Now, last but not least, it is worth mentioning those pointers again. Especially when working with structs, pointers can be important because without pointers, if we pass structs as a parameter to a function, for example, we always copy that entire struct. So we occupy extra space in memory, and we can save that by using a pointer. As a convenience feature, Go actually allows us to use the dot notation even on a pointer to save some extra time and avoid that longer form which we otherwise would have to use. We can avoid that because Go has this built-in convenience feature. And that's it for this introduction to structs. In the next course section, we're now going to practice working with them in a more realistic project, and then thereafter, we're going to dive even deeper into Go. Now let's build up on what we learned about structs in the previous course section, and let's apply it to a more realistic kind of project. Though project is still a big word, but nonetheless, we're going to apply what we learned in a different context at least. And therefore, in this course section, we are going to practice working with structs, of course, and specifically we'll again see how we can work with data that's stored in structs and how we can add methods to structs, so functions connected to specific structs. And as an extra bonus in this course section, we will also learn how we can use a built-in struct to write data into a file. Something we haven't done up to this point, but something we will do now in this section. Now for this section, I prepared a little starting project for you, which you find attached. To be precise, you find this practice Go file attached with some instructions and the very minimum base structure that we need. And you can simply drag that into one of your own projects, run the go mod init command to create a Go module with any identifier of your choice. And then you can use these instructions, which I put into that practice.go file, to practice working with structs. Though throughout this section, we're going to go through all these tasks together, so you can of course also just follow along with me if you don't want to practice this on your own right now. Now, if you do want to try it on your own, you find detailed instructions on what you should do here. I will just say that task number 5 will involve creating files and writing into files. And since that is nothing we did before, you can of course try it on your own, also with help of the official docs, looking for some built-in packages that can help you, but you can also ignore task number 5 and simply try to solve the other tasks. Because in these other tasks, you will need the knowledge you gained in the previous course section to create your own data type with the fields I'm mentioning here, to then create concrete instances of this data type in 2 different ways, which I lay out here, and to then output the data which you store in there, and to then also fetch some user input for creating these concrete instances and outputting that data. But again, it's all written down here. In the next lecture, we'll start implementing this together, and throughout the discourse section as a whole, we're going to solve all these tasks, and we're therefore again going to practice how we can work with structs and how structs do work. So, did you succeed? Let's now try this together. And of course, I'll start with task number 1, where the goal is to create a new type, a new data structure. So, in short, a new struct. We want to create our own struct which has 4 fields. And therefore here, below package main, above my main function, I'll create a new struct. You don't have to do it here. You could do it at the bottom of the file as well, but I prefer to define my structs up here before I then add logic on them later down in the file. And therefore, I'll create a struct as we learned it by using the type keyword and then any name of our choice. And since we'll describe a product as we might be storing it in an online store, I will name my struct type product. Now, when it comes to that first starting character, you can go for an uppercase or lowercase character depending on whether this type, this struct, should be available in other packages as well. For this practice project, we'll not have any other packages and will also not publish this package to the public, so it doesn't matter, and I'll go for the uppercase starting character here, but you can go for either of the two approaches. Then we need the struct keyword to finish this struct blueprint declaration, and now we can add the different data fields that should be part of that struct. And I did list those fields down there, though I did not mention which type of data should be stored in each field. But by looking at these names, you should be able to come up with fitting data types on your own. For example, if we start with the ID could be a number, an integer, if we want to assign IDs like 1, 2, 3, and so on. But it could also be a string, so that we can use any unique string to give each product a unique ID. And I'll go for the string approach here, and in my product struct, I'll add an ID field and set this to type string. Then we also need the title or the name of this product, and I'll set this to be a string as well. And then a description, and that's also a string because that will hold some text. Last but not least, here I will then also add a price field because that's what we wanted here as well. Now for the price, we definitely don't want a string, but instead a number would make more sense. And we could use an integer number if we assume that we have prices that have no decimal places. But in reality, we typically, of course, have prices that do have decimal places, and therefore I'll add float 64, or I'll set float 64 as a data type here. And with that, we defined our own product type here, our own product struct. And that's task number 1 solved. In task number 2, we should now use that struct to create concrete instances inside of the main function. And we should create them in 2 different ways. Directly in the main function, and then also in the main function with help of such a creation function, which I did show you in the previous course section. And we can use any values for those fields of our choice. So I'll do that here. I'll start with first product. The variable name is up to you, which I'll declare and initialize in one go with the := operator. And I'll create a new product instance here by using that struct literal notation, where we use the struct name and then opening and closing curly braces. And then you did learn that you can add values for those fields by targeting the fields by name, for example ID. And then with a colon, you can set a value, like first dash product as an ID for that first product struct which we're creating here. And then you can add a comma and add the next key value pair. For example, target the title or also the description and then thereafter the title. The order does not matter in that case when you are using those keys. But if you plan on setting all values anyways and you are fine with keeping the order, so the order laid out in that blueprint, you can also omit the keys down there and just set the values as a comma separated list. So first product as a title, as an ID, then as a title maybe a book, then as a description a nice book, and then last but not least, separated by another comma, the price, like $10.99, something like that. And I'll hit the auto format shortcut here, which actually formatted this there in a more readable way, but left that code here as it was. You can also split that across multiple lines if you prefer that. If that is what you want to do, you just have to make sure that you add a comma after the last value as well. And then I'll hit that auto format shortcut to make that more readable. And now we created our first struct instance. Now we should create two products here, or two instances in two different ways. And the second way involves such a creation helper function. And we did also learn about those functions in the previous course section. It's a regular function in the end, just a function that only exists to create structs with that struct literal approach. And therefore here, maybe below the struct, though again the exact position does not matter, we can add a new function and name it new product, following that naming convention where if we have a function that creates an instance of a struct, the function name should include new and then the struct name that will be created. And then here we can accept parameters that will give us the data that's needed for creating that struct. And that could be the ID, which is a string here, then the title, or just T if you want to shorten it, that is a string, then D for the description, and P for the price, which is a float. But you can also use longer, more descriptive parameter names. I'm just using these short ones here to keep this parameter list short and also to make it super clear that you don't need to use the same names as you picked here as field names in the struct. You can use the same names, but you don't have to. And then here in new product, I will simply create a new struct and then return it. And we can do this in one go using the struct literal notation here. And I'll insert the ID, the title, the description, and the price like that. And this will now return such a product struct. Now we just need to make it clear that new product will return a value of type product. And hence here after that parameter list, I define the type of the return value, which in this case is product. And we're good. Or we're almost good. This will now create a product struct and return it, but we're not returning the pointer, but the concrete value. And therefore, as emphasized multiple times in the previous course section, we will of course temporarily have two copies of this struct in memory. Now this is a super simple struct, not very complex, won't have huge pieces of data inside of it, and therefore creating a copy definitely won't be a problem. But still, we might want to return a pointer so that we avoid this extra copy altogether. Therefore, I'll change the return value type here from product to asterisk product to make it clear that we don't want to return the struct value itself, but a pointer to that value instead, so that that extra copy is avoided. Now we just have to make sure that we don't return the struct instance itself, but instead a pointer to it, so the address of that value. And we get that address here by using the ampersand symbol. We can do it like that, creating that product struct instance by using this struct literal notation, and then using the ampersand symbol to get the address of that value, and then to return that address overall. And now in the main function, we can create a second product by calling new product and now just passing some data for those parameters as parameter values, like second product as an ID, then maybe a title of a carpet, and then a description of a beautiful carpet. And then last but not least, the price, which could be 99.99. Like that. As a side note, if that's getting too long for your taste, you can also split that across multiple lines like that. This will be fine. You just should add a comma here at the end as well then. But then, after auto-formatting this, this again is a bit more readable. Maybe we even write it like this. So now we got both products created, both struct instances. The only important difference right now is really just that first product will be the struct value itself, whereas second product will be a pointer to a struct value. But we do have two different structs in memory now. And we do have two variables that will give us access to those structs. In case of first product, getting access is easy because the value itself was stored. In case of second product, we'll have to dereference it first in order to work with that struct value. Nonetheless, we did now create these concrete instances in two different ways. As a last step, we want to output the created data structures in the command line in the main function. And therefore, below these two variable declarations and definitions, I'll use the format package using the auto-completion to automatically add the import. And then here we can simply execute println. And to println, I'll pass the first product. And then I'll copy that and also output the second product, though, very important, that would be the address. If we want to output the value itself, we need to dereference it first by adding a star here. Alternatively, we could of course also dereference it here so that we store the value in second product. Then we don't need to dereference it down there. But I'm happy with storing the pointer here and dereferencing it here so that we also see this scenario in action. And now if we save everything and we quickly run our module, we see our two structs and their respective data being output in the command line. And that's now task number 2 solved. In task number 3, we now want to add a connected function. So a function that's closely connected to the struct that will then output the struct data. And we want to call that function from inside the main function then. So basically what we did here should now be put into a separate function that we can call here in main then. And such a connected function is called a method, as you learned. It's a regular function that also gets this receiver argument, which will be provided automatically by Go, and that receiver argument will give us access to that struct to which we tie the function. So therefore here, below the struct definition, I'll add a function which could be named print data or output data or whatever you want. And it's a regular function. It could also accept parameters, but I'll add that special receiver argument thing here in addition. And here we now specify the struct to which this function should belong. And in this case, that's the product. So I'll name this prod. The name is up to you. And set it to type product. And it's up to you whether you want the value here or a pointer. But I'll go for the pointer and hence add the asterisk, since that will avoid unnecessary copies. And in here we can now output the data. Now we could just use the println function again here and just output prod, or to be precise, dereference it and output it. That would be a quick and easy way, and if you did it like that, that's fine. But here I'll actually write a little bit more complex code. I'll use the printf function here to output the different fields with more annotation, so that I can say ID colon and then output the ID. And hence here I'll just point at prod.id. And I'll use the dot notation here for getting access to an individual field in that struct data package, which it is in the end. As a side note, we can use the dot notation here, even though this is a pointer, and therefore theoretically we should not be able to use it, but we can use it because Go gives us this shortcut and automatically dereferences this pointer for us. So Go automatically gives us this code if we use the dot notation on a pointer like that. It's a little convenience feature built in. And with that, we'll output the ID. And then I want to add a line break, which we can do by adding a /n. This is basically a special character representing a line break. And then I'll also output the title here, and therefore refer to prod title here. Prod title. And then also output the description here, and hence refer to prod description. And then also output the price, like that, price. And here we'll have a floating point value, and I want to limit the output to 2 decimal places, and therefore I'll use a little placeholder here, which we saw before in the course already. %.2f tells Go that we want to output a floating point value, but only the first 2 decimal places. And I'll also say US dollar and then the concrete value. And therefore here we'll refer to prod price. Now we got that print data method, as it's now called, since it has this receiver argument. And we can now call that method from inside main. Here, instead of calling print line, I can now reach out to the first product and call print data, and do the same for the second product and call print data like that. And if we now save that and then open that console again, if we run that code, that data is being output. Here's our first product data, and you see the price is nicely formatted. And here we got the second product data. So that's working, and that's a very complex, or a bit more complex, way of outputting the data. But that is now also task number 3 solved. In task number 4, we now want to make this program a little bit more interactive. Instead of just hard coding 2 products like this, we instead want to let the user of this application, enter some data through the command line. And that's of course also something we did before in this course already. So for that, we'll have to prompt the user for some input, and then add a reader which allows us to read that user input. And then we just need to create a struct with that gathered user input, and then again output that data as we did it before, but now based on the user input. For that, I will actually add a little helper function, which you don't have to do, but which I want to do here, which I'll name getProductInput, like this. And in here, I now first of all want to prompt the user by using print line and saying, please enter the product data. Like that. Then maybe, as we did it before, add a little separator here, a couple of dashes, just like that. And then we need that reader to get the user input. For that, just as before, I'll use the buff.io package, which is built into Go. And by using tab in the auto completion menu, it'll be imported automatically. And on that buff.io package, I'll call the new reader function. Now, this will actually return us a pointer to a reader struct. We worked with that before in the course, but there we didn't know it yet. Now we can actually understand that. The type of data we get back when we call new reader is a struct or to be very precise, a pointer at a struct. Now we also need to let go know where we want to read data, and here that will be the standard input, which is the command line. And for this we use the OS package, which will autocomplete to import it automatically. And on that OS package, we can call or we can reach out to standard input. So std_in. And that will now give us such a reader, or a pointer to such a reader to be precise. We can then use this reader with the dot notation to read string inputs, for example. And here reader is actually a pointer to a struct, but thanks to that Go shortcut I mentioned before, we can use the dot notation on that pointer and Go will dereference it for us. Alternatively, we dereference it manually, but of course there's no need to do that here. Now readString needs to know until which delimiter it should read the input, and that should be a byte. So we use single quotes and then here again the line break character /n to wait until the user hits the enter key. And that will then give us the user input here. Now actually we don't just need one user input, instead we need an input for the ID, the title, the description, and the price. And therefore to do all of that, I'll first of all prompt the user with print, not print ln, but just print, since I want to show that message in the same line where the user should enter the input, where I say product ID, :whitespace, and then prompt the user for some input and read that input here and store it in user input, or to be precise, maybe ID input. That might be a more fitting name. Now readString actually returns two values, but again we'll ignore the second value by adding a comma and this underscore, which tells Go that we're not interested in that other value right now. Now we got that ID input here, which will be a string. Now we can also gather the other pieces of data which we need. For example, the product title, and I'll name this title input and read it in the same way. And then again, I'll repeat that 2 more times to also read the product description and name this variable description input, and then also the product price and name this price input. Now we got these 4 pieces of input. Now, just as we did it before in the course, we'll have to clean them, get rid of the line break character, and then in case of the price input, also convert it to a float. Now, since we'll have a bunch of duplicate work here, we can actually also use some helper functions for that if we want to, and here I do want to do that. So I'll add a little helper function where I'll say read user input. And in that helper function, I just want to have that prompt text and a pointer to that reader, which we create here in the get product input function, so that we can use that reader inside of read user input. So the first value could be a pointer at that reader, and I'll name it reader, and the type should be buffio.reader. So the same type our reader is of here. And the second parameter which I expect here in read user input is the prompt text, which is a string. Here I'm not using a pointer, by the way, because passing primitive values like numbers or strings around is absolutely fine, and creating pointers, dereferencing pointers, and so on will simply be more work and maybe cost even more performance than just sticking to these default values and accepting a little bit of memory occupation. It's so little memory, it definitely won't matter. So for such primitive values like strings or numbers, you really typically don't want to pass pointers around. Instead, passing around values and copying values is fine here typically. But with that, we now got that helper function. And in here, I actually want to copy that code here where we get the product ID, pass it in here, and print that prompt text. Use that reader, which we get as a parameter, and get my general user input here, and then return the user input. And therefore, of course, I also want to make it clear which kind of value I return, and that will be a string. However, it should be a cleaned string, and therefore, I will actually override user input with a new value where I will use the strings package, which of course also should be imported here at the top. And that strings package gives us this replace function, which we saw before in the course already. Here we now pass in the string through which we want to search, which in this case is user input. Then pass in the string we want to search for, which in this case is the line break character. And then also the string with which we want to replace it, which in this case is an empty string. And then the number of times we want to replace it. And if we use -1 here, we'll replace it everywhere where we find it. But we should only find one line break. And then we return the cleaned up user input. Now we can actually reduce the code up there a little bit. Just grab product ID, get rid of that line, and really just say ID input is equal to read user input, pass the reader pointer, and then this prompt text. And then just replicate that 3 more times to also get the title input with this prompt text here, like that, and get rid of that code block. Then grab this prompt text and use that here to get our description input, like this. Get rid of this code here, and then get our product price here. So use this as a prompt text, get rid of this code here, and get our price input here. And now we reused some of that logic and avoided some code duplication. We're still not done though. I also want to convert price input to be a float, and we should use the colon =sign operator in all those places since we are creating brand new variables here. So that's something we gotta do here anyways. Use the colon =sign operator. And then convert price input, maybe with a blank line in between for better readability, by assigning a new value and using the strconf package, which we also used before in the course already, and which, just like all the other packages, needs to be imported. And then here in this strconf package, we'll find the parse float function to which we pass our string price input, and then the bit size. And here I want to parse a 64 float, and therefore I'll enter 64. And that will actually return 2 values. Again, I'll ignore the second one. And we'll have a problem that this, of course, now returns a float value type, not a string. So reassigning it to price input will not be an option. Instead, I'll name this price value and create this as a brand new variable by adding the colon again. And now we are fine. And now overall, we can return all those gathered inputs. Here, getProductInput may now return those different pieces of data. Or we already create the struct here and just return that struct. That would also be an option. And I'll actually do the latter so that we also practice this, though it is up to you which approach you want to use. Here, I'll just create my product by using that new product helper function, and I'll pass ID input, title input, description input, and then also the price value, so the float, as parameter values to this creation function. And then I'll just return this product struct in the end. Or to be precise, that pointer to that struct, which it actually is. Now we just need to adjust get product input and make it clear that this will return a pointer to a product struct by adding the asterisk product here as a return value. And maybe we now rename this to just get product because we don't just get the input, we actually get the entire product data package in the end. So get product sounds like a more fitting name to me. With all that done, we can get rid of our dummy struct data here in the main function and instead add a created product variable, that sounds like a fitting name to me, and call get product here. And the created product then is a pointer at that created struct, and therefore we can now of course also call print data on that created product. And with all that done, with all those changes made, if we now save everything and open up that console, if we run our program, we should be prompted to enter some product data, like a computer, give it a title of a computer, a great computer could be the description, and give it a price, and hit enter, and our data is being output here. So this all seems to work. And with that, we're now combining what we learned before in the course, how we can read user input, with our newly gained knowledge of working with structs. And along the way, we also learned that this reader with which we are working is also a struct built into Go. We used it before, but there we didn't fully understand it. Now we do understand how it works internally, or which kind of data it is internally. Now with that get product function on which we worked, we solved task number 4. Task number 5 now is a bonus task because here we'll have to do something which we never did before. So if you did not solve this, that's of course absolutely fine. We'll now solve it together. Because here I now want to add another connected function to my struct, so another method, which should be called store, which actually does not just print data to the command line, like the print data method does it, but which instead writes data into a file. And that is of course something we haven't done before. Now the file name should be the unique ID which we assigned, and therefore of course we should make sure that we do assign an ID that can be used as a file name. And then we should call that function at the end of the main function. So therefore, let's start by defining this method, and I'll do it right below my struct again. I'll add it as a brand new function, because that is what a method is, as you learned, and I'll name it store. Now to turn it into a method, we add that receiver argument, and again here I want to get a pointer to that product struct. Now in here, I want to write the struct data to a file. And for writing data to a file, it's again the OS package, which we are already importing, that can help us. OS stands for operating system, and here we got access to common operations like changing directories, and also creating files. For that, we got the create function here, which will create a file in a certain path with a certain name, and it will then give us access to that file by returning a pointer to that file. It also returns another value, which again won't matter to us here. So I'll execute create here, and now we need to pass in the file name as a string. Actually, the file name can also be a path to some nested folders if we need that, but here I'll just specify a file name, and the file name should actually be prod.id, because we want to use that unique ID which every product has as a file name. Now as mentioned, we'll get back a file then, and the second argument which we'll ignore, and we can then use this file struct or this pointer to this file struct, which we get back to work with that file. To be precise, on that file struct, we'll have a write method and also a write string method, which allows us to write some string data into that file. And we can use this method to write our content into a file. For that, I want to prepare the content of the file first of all, and I'll do that with help of a brand new variable. And I'll use the format package to use the sprintf function, which will not output a string to the command line, but which instead returns a formatted string. And I'm using that so that I can create a string here, which has the formatting I'm using down there, which then will be stored in content. Now here, I want to output the same kind of data I have down there. I'll just now put it all into one string. So I'll start with the ID, then with the title thereafter, then with the description thereafter, and then with the price thereafter. We can also write this as a multi-line string by not using double quotes, but instead backticks. So not single quotes, but backticks. That's a special character on your keyboard, opening and closing. And if you use backticks, you can actually write multi-line strings like this, so that this is a bit easier to read for you. But I'll stick to the double quote version here like that. And then just add a comma and add the different values that should be plugged in here for these placeholders. And that will of course be the prod ID, the prod title, the prod description, and last but not least, the prod price. And I want to make this a bit more readable, so I'll add a couple of line breaks here after all these parameters, and also here, and hence add a comma, and also add that into a new line, so that this is a bit more readable. And now it's this content, which is this formatted string, which I want to write into my file, so we pass that to write string as a value. That should now write that content into a file, and as a last step, whenever we write data into a file, or whenever we work with a file in general, we should also close the connection to that file once we're done by using file.close. This ensures that we, well, save that file, so to say, and we stop editing it. With all that done, we got the store method. Now we just also need to use it. And for this, in the main function here, we can still print our data, but I also want to use my created product and now call store. And with all of that, if we now open the sidebar, we should soon see a new file, and we can now open the terminal to run our program and then start entering some data, like a book, product title is a book, description is a nice book, and price is $9.99. Now we see the output here, and we also see a book file, which we can click on, and we see our data in there as well. Now the file has no extension because I haven't added one. In the store method, we can also add an extension here where we create the file name. We can concatenate an extension like .txt if we want to. If I do that, save everything and run this again, I can add my carpet now, maybe a carpet, a nice carpet, and then my price. And now we will also see that we got a text file here. Content, of course, is the same. I mean, it's different content, but the same structure and logic. And with that, I'll delete these two files, but we did now solve task number 5. We now also saw how we can write into files. As you can tell, it's not too difficult, and we thoroughly practiced working with structs.